Section 11.7 is about the binomial theorem. We're going to take a look at binomials when we expand them. In other words, if I have a plus b squared, that's really a plus b times itself. And then if I distribute it, I get this polynomial. If I do it 3 times and I distribute, I get this one and so on. So there's a pattern here that I want you to recognize, and we're going to look at some of the things that we notice when we expand binomials. The first thing we're going to look at is there are n plus 1 terms. If n is the exponent, in this case of 5, notice there are 6 terms. When the exponent's a 4, there are 5 terms and so on. So you can see that in the pattern. Also, the exponent n is the first exponent on the a value here, and it's the exponent on the b value at the end. So it's the same exponent on the first term as it is the last term. Also notice that in each term, the exponent of the a's go down. So here it's 5, 4, 3, 2, 1, and then there's a 0 exponent on this a. But they go up for the b's, 0, 1, 2, 3, 4, 5. The sum of the exponents is always n, so when you add them all up, you always are going to get a 5 when you add the a exponents and the b exponents. And then the last thing to notice is the coefficients are symmetric. There's a pattern here. The coefficients are 1, 5, 10, 10, 5, and 1. If we go to the fourth power 1, it's 1, 4, 6, 4, and 1. There's a pattern there that is symmetrical. Here we have our binomials all expanded again, but if you notice, if you write them this way, they form a triangle. If we just look at the coefficients in that triangle, we come up with this thing called Pascal's triangle, because the mathematician Blaise Pascal is the first guy to have noticed this. And that is the coefficients of the terms that are displayed in a triangular pattern. So if you look, here's the expansion once again, but I've taken out the a's and b's, and so you just see the numbers. A couple things to note about Pascal's triangle: each row begins and ends with a 1, and that each coefficient is the sum of the 2 coefficients above it. So you see here this 10 comes from a 6 plus a 4. And it works that way for all of the coefficients in Pascal's triangle, except for the ones on the ends. Here I'm asked to take this binomial x plus y and bring it to the 7th power and expand it out. Well, in the last 2 slides, we've seen expansions of binomials up to the 5th power. So I'm going to take my Pascal's triangle from the last slide, and I'm going to add a couple rows, because if I were to find what a plus b to the 6th power was, then I would know the coefficients of this to the 6th power, and the same for the 7th power. So I'm going to add another row to the triangle here. And remember, we're going to add the 2 above to get the next row. So 15, 20, and 15. And then to make the next row, I'm going to get these values. So by expanding Pascal's triangle, we now are finding what happens when we have a binomial to the 6th power and a binomial to the 7th power. These will be the coefficients of that binomial. Now, just because this shows a and b doesn't mean I can't do the same thing for x and y. So x plus y to the 7th power, and I'm going to do it on a new row because it's going to be pretty long. It's going to start with a coefficient of 1, because that's what Pascal's triangle shows. And it's going to have an x to the 7th. Because remember, on the first slide, we said that the first term always has an x, or has a value of the 7th power, and then it's going to decrease, while in this case the y increases. So now we use a 7 for the next term, but the x is going to go down by 1, and the y is going to go up by 1. And we continue this pattern using these numbers as our coefficients. And so this is what we have. Notice the coefficients are the same as they are in the triangle. The x's go down by 1 each time, and the y's go up. So this is what x plus y to the 7th power would be expanded out. So now that we've seen what the binomial expansion looks like, it leads us to this thing called the binomial theorem, which says if you have any binomial to an n power, you can expand it out using this pattern that you see here. And it looks real complicated, but I'm going to try to walk you through this example so we can do it. So here we have a minus b. Understand there's an a and there's a negative b here, so that's going to change a couple things when we go through it. but I'm looking for the sixth row of Pascal's triangle. So if I go here on the last slide, this is the sixth row. So these are the coefficients that I'm going to use. So all of my coefficients on the next slide are going to be from here: 1, 6, 15, 20, 15, 6, and 1. So when you're wondering where those come from, this is where I'm getting them from. So we'll start by having the coefficient of 1. We're going to have a to the 6th power and b to the 0 power, because that's what the first term looks like. Then we're going to look here at this one. This is the one I'm on now. I'm going to take n over 1. Well, n is 6, so this is going to be a 6 over 1. I knew that because of Pascal's triangle. I'm going to drop down the exponent of the a, and I'm going to increase the exponent of the b. So there's my second term. My third term is going to be n, which is 6 times 5, n minus 1, and that's over 1 times 2. I'm going to take the a and bring that down an exponent, and I'm going to increase the b. And that's what we're doing here. The next term is 6 times 5 times 4 over 1 times 2 times 3. I'm getting that from right here. Bring the a down and bring the b exponent up. And then I'm going to continue with the same pattern. Now, these values in the middle here, we can calculate what their values are. 6 times 5 is 30, divided by 2 is going to be a 15. So we know that this is going to be 15. We know this is going to be 30 times 4 is 120, divided by 6. So that's going to be a 20. And we know this is going to be a 15. Now the next thing I want to talk about is the fact that the b has a negative in front of it, which means this technically should be a negative b. This one's a negative b also, but when you square it, it becomes positive. This one is a negative b, which means it's going to go negative. This one's a negative b, but when you do to the 4th power, it'll be positive. And this one's a negative b, but to an odd power will stay negative. Oh, and there's one more. This one's a negative b, but to the 6th power, it's going to be positive. So as I write the whole thing out, I'm going to get an a to the 6th. This one's going to be a minus 6a to the 5th b. The minus comes from the negative b there. Plus 15a squared b to the 2nd. The reason it's a plus is because the b is being squared. Minus 20 a to the 3rd b to the 3rd. The reason it's minus is because the b is to an odd power. 15a squared b to the 4th with a plus, minus 6ab to the 5th power, and then finally plus b to the 6th power. Now I want you to notice these numbers can be calculated using the binomial theorem, but if you know the numbers in Pascal's triangle, like I did in this page, 1, 6, 15, 20, 15, 6, and 1, you know what the coefficients are going to be. You don't even have to do the calculations there. Here we're going to define what a factorial is. Factorials are the product of an integer and all the integers below it. And we use an exclamation point to represent factorial. So what you see here is called 4 factorial. And what that means is 4 times 3 times 2 times 1. You multiply the 4 times all the numbers that come in front of it. So 7 factorial, 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what a factorial means. You multiply by all the numbers that come in front of it. Now why is that important? Because if you go back to the binomial theorem and you look here, n times n minus 1 and n minus 2, if n is a 6, then this is 6 times 5 times 4. And if you look down here, 1 times 2 times 3 is also 3 times 2 times 1. So that can be written as 3 factorial. So there are times when we are going to use factorials to rewrite parts of the binomial theorem in a smaller, more concise way. So here's an example using factorials that we're asked to evaluate. 8 factorial divided by 3 factorial times 5 factorial. Let's see what that looks like. 8 factorial is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. That's what 8 factorial is. And then 3 factorial and 5 factorial, I'll write those out. 3 times 2 times 1. and then 5 times 4 times 3 times 2 times 1. And let's simplify this. Well, hopefully you can see that the 5, 4, 3, 2, and 1 can all cancel, because you're multiplying and you can cancel things. You can cancel factors that are alike on the top and the bottom. Here we can simplify. 3 goes into 6 twice. 2 cancels with that 2, and we get 8 times 7 over 1, which is 56. So here you see the same exact binomial theorem that we looked at before, except now we can use factorials to write it. Instead of saying n times n minus 1 and n minus 2 and so on, we can just say n factorial over n factorial times 0 factorial. And we can write it out this way. Furthermore, we can write it in sigma notation by writing it this way, because this is a sum that has multiple terms. So I'm going to use this idea, the factorial form, to expand this binomial to the 5th power. So I'm going to use this one right here. I'm going to use the sigma notation, and this is my binomial. So my n is 5. It's going to go from 0 to 5. And I start by taking my n with a factorial. So I'm going to do 5 factorial over n, which is 5, minus k. Since my k starts out being a 0, this will be 5 factorial, 0 factorial, times the letter a. Now I'm not using a in this case. My a is a 2x. So I'm going to take 2x to the 5th power, and I'm going to take y to the k power, which is 0, so I'm not going to write that down. So this is my first term. So my next term again has n factorial over n minus k. K is now a 1, so this will be a 4 factorial times k factorial, which is 1 factorial. Again, times the 2x to the 4th power, because we drop it, but now we take the y and bring that to the 1st power. Next term again, 5 factorial, but then we do 5 minus the k now of 2, so 3 factorial, 2 factorial. I still have the 2x, drop it down, and then take the y and bring that up. So hopefully you're starting to see the pattern now. So 5 factorial here, n minus k, k is now a 3, so 2 factorial, 3 factorial, times the 2x, drop that down to the 2nd power, and increase the y to the 3rd power. And that's plugging in all my n's and k's. Now let's expand the whole thing out and see what it finally equals. Well, 5 factorial over 5 factorial will cancel, leaving just a 1. So this is really 2x to the 5th power. 2 to the 5th power is 32 x to the 5th. In this one, 5 factorial over 4 factorial. Well, you know 5 times 4 times 3 times 2 times 1 over 4 times 3 times 2 times 1 will cancel everything except the 5. So this will be a 5 times 2 to the 4th power, which is 16 x to the 4th, and we'll further simplify that to be 80 x to the 4th. Y. We forgot the y there, so we'll put that in. Next term, 5 factorial over 3 factorial times 2 factorial. So the 3's will go, the 2's will go, the 1's will go. This 2 will cancel with this 4, leaving a 2, so it looks like a 10. So this will be a 10. 2 cubed is 8. X cubed, y squared. Further simplifying, 8 times 10 is 80. X cubed, y squared. So that's what this entire binomial right here to the 5th power is, expanded out by using the sigma notation and the factorial form of the binomial theorem. Here we're told that the k value is always going to be 1 less than the number of the term that you're finding. So if we're asked to find the 5th term of this binomial expansion, then that means we are going to use a k value of 1 less than that, which is going to be 4. So I'm going to write out my sigma notation for p plus q to the 10th power. So this is what it looks like for the 10th power, but I'm looking for the 5th term now. And because I'm looking for the 5th term, k is going to be one value less than that. So k is going to be a 4. So then I'm going to put this in 10 factorial over 10 minus 4, which gives me a 6 factorial, times a 4 factorial. This will be p to the 10 minus 4, which is 6th, and q to the 4th power. Now I just got to figure out what this number is. So here's what all the factorials are written out. If I take the 6 down to the 1, those will cancel. 4 will go into the 8 twice, and then that will cancel with the 2 down here, and the 3 will go into the 9 3 times, leaving just a 1. So I have a 7 times 3 times 10, which is 210, and then we have p to the 6th, q to the 4th. So this is what the 5th term is in this binomial to the 10th power.